So we're in Chapter 2, Section 3 of your chemistry book. And now we're going to talk about subatomic particles. You know, originally we talked about Dalton and his atomic picture, and that atoms were these little hard spheres. But now in the late 19th and 20th centuries, we found that now atoms can be broken down into smaller parts. And these smaller parts have a particular something to do with electricity. Eventually, the atom was shown to be made up of smaller parts of matter, and these smaller parts of matter are called subatomic particles. So what subatomic particles are found? Well, we have protons and neutrons, and they're in the nucleus of the atom. And they're the major mass of the atom. And then we have these unusual, smaller, little light that travel around the atom quadrillions of times per second in very unpredictable patterns. And they're going to be calling these electrons. And they have to do with electricity, and we'll find out how. So how did they discover these things? And that's what we're going to talk about in this section, is the discovery of these subatomic particles. We're going to start with the electron. Well, in the early 1800s, we have Sir Humphrey Davy, who lived 1778 to 1829, and Michael Faraday, 1791 to 1867. And they used electricity to decompose chemical compounds. So they knew something about these electrons. And they knew there were electrical forces that would hold elements together, but they didn't know much else about them. And then we have George Stoney, and he lived in 1826 to 1911, and he proposed that the units of electrical charge, they were negative charged particles, were associated with atoms. These electrons had to do with atoms, and he named these particles in the atoms called electrons. From the Greek electron, E-L-E-K-T-R-N, meaning amber, because that's what they used to call it when you would take some silk and you'd rub it on something, and all of a sudden you get this static electricity and these little sparks. They would call it amber. So he called them electrons, and he said these electrons were in all different atoms, and they were causing these. So let's find out more about these electrons. Well, then came what was called the cathode rays. This is very unusual, let's say, because they were studying electrons with these cathode rays right here. We'll be looking at this here, the cathode ray tube, and they didn't even know what they were studying or doing. And in 1859, they took these two electrical leads and they removed the air from this area, and strange things began to happen. There was a high source of electricity going on. It was like these invisible rays emanated from the cathode, the negative side, toward the positive side, the anode. And the air began to glow. See this picture of the cathode rays? The air glowing towards these. And they're like, what in the world is going on here with these invisible rays? And these were discovered by Julius Plucker in 1859. And he basically called this tube the CRT. So you need to know about this on your test. What is the CRT? What is this tube? The cathode ray tube was where they actually found these atoms were behaving weird in an electrical type way here. So, and on to Sir William Crookes, and he lived in 1832 to 1919. And he basically, this is a picture of Crookes' versions of the cathode. He kind of made it a little bit different than the original one, but the cathode rays missed the anode and struck the end of the tube, causing it to glow. And the objects then cast shadows there. And he speculated that they were particles of some sort, doing this, but he didn't really know. And that there was some properties regardless, and trying to figure out how. And he even reflected by a magnetic field. So he knew some things were going on, and that he figured that things were going on with these electrons, but he didn't really put it totally together at this time. So we went on to, well, before Millikan, we went on to J.J. Thomson. And J.J. Thomson, he basically demonstrated, he lived 1856 to 1940, he demonstrated that they are composed of negatively charged particles. The electrons that Stoney had proposed years before were a negative charge. So, and basically, he said that all of these electrons are in all matter. And Thomson, J.J. Thomson, proposed an E, which is electron, to mass in 1897. He did this experiment with these cathode rays and the electric and magnetic fields, and determined this E to M here. Let's see. Okay, here we go. E to M measurement, and these this E to M measurement, and then on to Robert Millikan, and he used the X-rays to knock electrons off atoms in oil droplets. Let's go back up to that one first. There's the one with the Millikan's oil drop experiment. You can see how, wow, you know, how the oil droplet under the study and these oil droplets, and he would knock these oil droplets, basically these electrons, off the oil droplets and fill the electrical field there. See, it would fill with electrons. And so he'd say, what is this? And he determined there was charge and mass, and then he figured that electrons were very lightweight. And in fact, they'd be 9.1094 times 10 to the negative 28th power, you know, so we're talking about, he was thinking they're very, very light compared to the mass of an atom, you know, so. So going on to here, let's go down here. This is a candle ray tube. We're going to be talking about this in just a little bit. So not only electrons were being discovered, but protons were being discovered. That atoms, you know, basically atoms are electrically neutral. That they must contain positively charged particles, then they must contain electrons or negative charged particles. And so they knew that if they had electrons, they must have positive charge. And so a man named Eugene Goldstein, and he was a German guy, and he lived in 1850 to 1930. And he, in addition to the negative cathode ray, the CRT produced positive rays that flow in opposite directions. He had canal rays, and here's a picture of his. High-speed electrons, cathode rays streaming from the cathode tube to the anode knock electrons from the gas molecules, creating streams of positive ions that are attracted to the cathode. You see how? So now he has these cathode rays that are coming, and they have the positive ions that are attracted to him. And here we have the holes of the canals in the canoid allow ions to pass through and strike the opposite end of the tube, causing the glass to glow. So we're going with Eugene Goldstein here. And then again, William Wayne and J.J. Thomson again, discovery of protons were equal and opposite to electrons. And then they discovered that the mass of the proton was a lot heavier, 1.673 times 10 to the negative 836 times, or 1836 times more than an electron. So these electrons were very tiny, and then of course the positive protons in the nucleus were a lot heavier. So they could figure this out. And then Ernest Rutherford, he was another one of these scientists that basically said protons are a component of all matter. And actually, he's one of the first ones, I think, that made the planetary model of what an atom looked like, you know. So let's go on to the next page. So the nucleus now. So how did they figure out what was in the nucleus? Well, shortly after his measurement of the EM for the electron, J.J. Thomson again proposed the model of the atom shown in figure 2.18. This is his model. Does that look like it was right? Not really. This here. He called this model basically like a plum pudding model. And that's the way he started. But later on, he would be disproved that this could not be the model of the atom. He just thought the electrons were here, and there was a sphere of positive charge here, and it looked like all mixed in like a plum pudding, which later on was disproved until Hans Geiger and Marsden's experiment here. And you can see their experiment there. They had high-speed helium ions that they put through, and as they put through, it separated these ions into these subatomic like bullets that bombarded here at the end. So they saw, okay, the whole thing, this whole plum pudding can't be. Basically, these electrons must be on the outside, is what they're thinking, right? And so we're thinking about how a few of the ions here were deflected back towards the source, and which made the plum pudding thing impossible, as they showed forth this experiment. They said that it had to be a small central nucleus that contained virtually all of the mass in the nucleus, and it had to be positive charges there. And then the negative circle about the negative charges would circle about the nucleus. So basically saying that these electrons had to be on the outside circling around. And this model would now be called the nuclear or planetary model, so which would be totally different, kind of model, totally different than the plum pudding, right? A different model totally than what was before. So basically going into the nucleus, so now they knew the nucleus would be like the size of a tennis ball, and the electrons could be more than a mile away. So if you had this nucleus as just a tennis ball, the electrons would be orbiting miles away. That's how much distance there would be between the electrons and the nucleus in an atom, but an atom's very tiny, of course. So if this nucleus with these atoms would be like a large sports stadium, and the nucleus would be the size of a marble in the sports, and the electrons would be whizzing around the outside of the stadium. That's quite a deal. So the discovering of this, let's see, no, I didn't see, let me go and see if we have another picture of that maybe. Here would be the picture. Now this is not a right picture. Here's the picture of the relative size. So here we'd have this tiny marble in the midst of a whole stadium, and the electrons would be going around and around the outside of it. Let's go back to that one picture. Wasn't sure if we went over that picture that I just missed right down here. So these were the high speed. This is that exclamation of the gold foil experiment. It's not to scale there, but here we have this foil experiment that with the gold foil here that we were talking about earlier. Let's see. So basically the high-speed helium ions are going through, and as they're going through, they're deflected, but not that much, which means there's not very much space in the midst of all of these. As the electrons were going through, it was very rare that some would be deflected. Only the ones that would hit the nucleus would be deflected. Otherwise, they'd go right through. So that's why they found out there's a lot of space in an atom. Now let's go over to the discovery of the neutron. So the neutron's discovery, Rutherford proposed the existence of a neutral particle in the nucleus. So he said, not only do we have protons, we're going to have other things. And these other things he thought were neutrons. So basically, the neutral particle would be very difficult to detect. The only way they detect this particle would be by the mass of the nucleus, right? So here's the Rutherford model of the atom. So this is, I think, a test question, maybe a quiz question, is that who did the planetary model? Who gave us this model? Rutherford did. So he said basically here you see the protons and neutrons in the middle, and you see the electrons going around, similar to our model that we have today. So in 1920, Rutherford proposed the existence of a neutral particle in the nucleus having a mass approximately equal to that of a hydrogen atom. His model, taking all three subatomic particles into account, is diagrammed there, as you see there. A neutral particle, such as one as Rutherford postulated, would be difficult to detect, as I said, And physicist Sir James Chadwick concluded and demonstrate the existence of such a particle he would call later on a neutron. He also determined the mass of the neutron to be 1.675 times 10 to the negative 24th, just a little bit heavier than a proton. So protons would be, here we have the protons, or the green ones, they'd be positive charge. Neutrons are neutral, and electrons on the outside. In summary, the atom is mostly empty space. At the center is a small, very dense nucleus, right? And this small, dense nucleus is surrounded by as many electrons as there are protons. So that's why it's neutral, because as many of these green ones, there'll be electrons. Electrons are negative and protons are positive. And so then the whole atom would be neutral, right? So let's look at the table here. Here's the table. So let's look at the table. Has the table talking right here about electrons. Here's the symbol for electron is E. Here's the symbol of proton P, neutron N. Here's the size, and I went over these sizes before. You can see that the electron is so much lighter as negative 28th power, and these are negative 24th power. And the neutron is just a little bit heavier, hardly much, but a little bit heavier than the proton. So, and the electron is outside of the nucleus, going around it, and then of course the proton and neutrons are in. So, and the charges here, we have, of course, the electron is having a -1 charge, proton is a +1 charge, or a positive charge, and the neutrons are neutral with 0 charge. So, need to know that. Those are all test questions, and now that we know about protons and neutrons and electrons. But guess what? Let's go on just one more page here, and we're going to find, there's also now, we found quarks. You know, when I was in chemistry, we never studied quarks because we never knew about this. This is pretty new. So, so it was always thought that protons and neutrons were indivisible, but now they can be split into even smaller things. And so they discovered that protons and neutrons can be split into fragments using this powerful particle accelerators. That's what we have. They called atom smashers. They could smash these atoms, and then they could actually get them to another smaller thing called a quark. So, but most scientists now think that protons and neutrons are the building blocks of the atom's nucleus, are actually composed or even smaller, these smaller quarks. And there's the up quarks and down quarks, okay, as you can see in the picture. So each of these quarks is about 1/3 of the mass of a proton or neutron. The up quark has electric charge of +2/3, which means a positive charge, while the down quark is a -1/3 charge, you know. So it takes, according to the quark theory, it takes 3 of these quarks to make a proton or a neutron. So, and these quarks, we have their up and down there pictures. A neutron is composed of up quark and 2 down quarks. The quarks' electric charges cancel, making them neutral. And then, of course, we have the other way with proton. So here you can see the picture here. So here's the quarks. You have an up charge of 2/3. That means positive 2/3. And you have a up quark, quark of a 2/3, and a down quark of a 1/3. So now the proton is going to be charged because it has 2 charged positive quarks. Now, the up quark here is 2/3, and now you have a down quark, which is only 1/3, another down quark, and now this balances out where there's no charge. These are quarks. Now, who knows what exactly quarks do but to give their charges? Who knows? And the Bible says that actually that Jesus holds everything together. So it's pretty amazing to be able to find these things. Now we're going into quarks, you know. So let's go over the questions just a little bit here, if you can know. What negative charged particle was discovered through the study of cathode rays? Electrons. We know electrons, they're negative. What positively charged particle was discovered through the study of canal rays? We know those positive charge are protons. What is the dense central core of an atom called? A nucleus. What two types of subatomic particles are found in the dense core of dense core of the atom? In the dense core of the atom, you find the neutrons and the protons in the nucleus, right? According to current theory, protons and neutrons are composed of what type of smaller particles? Quarks. So you need to all know all those because those will be test questions for sure. So that's enough for this, and then we'll go on to atomic number, mass number, isotopes, and ions in the next video.